Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, how are you today? I hope you are in such a good condition. Today, we meet on first Tangerang International Conference, and due to pandemic condition, the conference will be held by video. I am Dian Nuramdiani, delegated for Radiology Program Study Al-Islam Politeknik of Bandung, and in this special occasion, I would like to share the result of my latest research concerning estimation of radiation dose in adult patients for X-ray thorax diagnostic examination. Enjoy the video. The title of the research is Estimation of Radiation Dose in Adult Patient for X-ray Thorax Diagnostic Examination. With the authors consists of first one is myself, Dian Nuramdiani. Second one is Oktarina Damayanti. Third one is Liz Relianti Arum. Fourth one is Lily Julia Rahmat. And fifth one is Suwandi. We are from Radiology Study Program Al-Islam Politeknik of Bandung. Introduction. According to the data displayed on the Bapeten website, in April 2015, there were 5,665 permits for X-ray machine, 99 permits for radiotherapy facilities, and 32 permits for nuclear medicine facilities, with a total of 4,736 workers involved in those fields. This data illustrates that the utilization of radiation in health sectors has spread widely. The United Nations Scientific Committee on the Effect of Atomic Radiation states that the largest share of radiation application in the health sectors come from X-ray exposure in routine diagnostic radiology examination. The data also show that in 2000, the number of routine diagnostic radiological examination performed worldwide was reported to be about 1910 million and kept increasing to 3,100 million in 2008. As a consequence, there were also increases in collective effective dose from 2.3 million mensievert to 4 million mensievert, and in the per capita dose of 0.4 millisievert increased to 0.6 millisievert. In addition to providing great benefits, the use of radiation in the medical world also carries a dangerous risk for the safety of patients, staff, and society if it is not monitored properly. Measurement of radiation dose on patients undergoing radiodiagnostic examination is one of the radiation protection to prevent the determinative effect and stochastic effect from the radiation. The dose received by patient is usually expressed in terms of intense surface area, ISEC, or intense skin dose, ESD. Direct measurement can be made using a personal dosimeter, like pocket dosimeter, film badge, or TLD, on the patient radiation object under certain irradiating conditions. But in fact, the measurement of the exposure dose is not always carried out to patients who perform the examination. The unavailability of a personal dosimeter to be worn by all patients during the examination, it is based on the assumption that the patient interaction with radiation is not as intense as that of radiation workers, so that the radiation dose on the patient body is much lesser than the workers. However, patient safety must still be prioritized by measuring the radiation dose as a form of radiation protection enforcement effort. One of measurement of the patient estimated radiation exposure dose without the use of a personal dosimeter is use CalDOS-X. CalDOS-X is a software providing a possibility to calculate incident air kerma and entrance surface air kerma, two important quantities commonly used in X-ray diagnosis, based on the output value of the X-ray machine used. Besides that, the software uses conversion coefficient to assess the absorbed dose on human organs and tissues, the effective dose, and the patient cancer risk from radiographic examination. Therefore, this study is necessary to evaluate and ensure that the estimated dose reset by the patient is below the reference dose. Research method. This study used mixed method combining quantitative and qualitative data analysis. Quantitative data was obtained from the calculation of the estimated dose value through the use of CalDOS software to be further analyzed qualitatively by comparing the estimated dose with the dose value set by Bapaten. Calculation of the estimated radiation dose was carried out on 40 radiodiagnostic examinations using various exposure factors. The examination focused on thorax examination with anterior-posterior (AP), posterior-anterior (PA), and lateral RLAT/LLAT projection. The measurement of the estimated dose was calculated using CalDOS-X software on phantom of FACS06 and MAX06 having a voxel size of 1.2 mm3, whose organ and soft tissue mass fitting the reference data from ICRV89. Variation of exposure factor, especially to potential, which were used in calculating the estimated radiation dose received by the patient on thorax examination, use a range value according to the default CalDOS-X software of 60 to 150 kV for PA and RLTA/LLTA projection, and 60 to 120 kV for AP projection. Meanwhile, the variation of FDD or focus to detector distance that can be used in range from 120 to 220 cm was for PA and RLTA/LLTA projection, and 90 to 120 cm was for AP projection. As mentioned before, that in this study, the radiation dose produced is expressed in incident air kerma, INEC, and intern surface air kerma, ISEC. INEC is kerma in the air that come from X-ray irradiation in the middle of the phantom position without taking into account the backscatter factor. It is needed to determine the ISEC value with the relation between the three quantities as stated in the following equation. Result and discussion. To obtain ISEC value, INEC was previously calculated as the radiation output of the X-ray machine. The radiation output in this study was obtained as shown in the following table and graph. The X-ray radiation outputs in Table 1 and graph show the values of radiation exposure or air kerma in the X-ray main beam measured in free air at a certain distance, usually 100 cm from the focus without backscattering contribution. Each X-ray machine has different radiation output graph, and this uniqueness occurred because each X-ray machine can have different filtration, HPL, KVV, and MAS. As mentioned by Bapoten, that the radiation output value on X-ray radiography is influenced by tube voltage, current strength, irradiation time, distance between points focus with the object of observation, and total filtration, the number of inherent filters with additional filters. Based on the graph, the radiation output equation is Y equal 0.0419 to the power of 1.7744, or can be written like equation below. The equation is similar to the literature, explaining that radiation exposure in diagnostic is proportional to the square of the KV value. Furthermore, the INEC equation obtained can be used if the parameters of the value of KVV, MAF, and the distance from patient to the focus of the X-ray machine in the equation are met. With correlation coefficient value of R square equal 0.9978 and tube current time which tend to be constant, they strengthen the linearity of correlationship between tube voltage and X-ray radiation dose output. Table 2 shows the data of the calculated dose estimation from 40 thorax examination consisting of 19 or 47.5% examination of PA projection, 9 or 22.5% examination of lateral projection, and 12 or 30% examination of AP projection for the supine position. The number of patients involved in the examination were 52.5% male and 47.5% female from 25 to 60 years old. The tube potential variation used was in the range of 60 to 120 kV with an average value of 22 kV. The tube current variation was in the range of 5 to 10 mA/s with an average value of 6.275 mA/s. And variation of FDD was in the range of 100 cm to 200 cm with an average of 147 cm. In addition to the default, the selection of tube potential values, tube currents, and FDD took into account the references standard value of the exposure factor commonly used in thorax examination in one of the radiology lab, as well as the estimated thickness of the patient of about 20 to 40. As it is understood that INEC is air kerma without backscattering, so to get ESEC or ESD values, INEC values must be corrected with backscatter factor. In Table 3, the INEC value that had been obtained was then multiplied by the BSF value. And here are Table 3, summary of those estimates of INEC and ESEC for all thorax examination. The BSF value in question has the smallest value of 1.29 and the largest value of 1.44 with an average value of 1.357. The BSF value in this study fits the reference from the IAEA Technical Report Series number 457 of 2007, stating that the backscatter factor for radiograph has a value ranging from 1.24 to 1.67. The generally accepted international assumption of backscatter from patient is approximately 1.35. The exact value in this study could be evaluated through comparison with several existing references. One of them is the dose reference level value set by Bapeten. For adult of 0.3 mg for thorax PA examination, 0.44 mg for thorax lateral examination, and 0.95 mg for thoracic supine AP examination, as shown in Table 4 below. Table 4 consists of comparison among the estimated radiation dose value obtained in the study and the DRL value determined by Bapeten in 2020, as well as the dose value from several previous studies. Table 4 shows that the estimated dose value obtained in the study for the PA and lateral thorax examination were above the Bapeten DRL values. But for the supine thoracic AP, the dose value obtained were below the DRL values. Similarly, when compared to the dose value obtained from the result of previous studies, the AP and lateral thorax examination tend to be above of the other dose values, and the supine AP thoracic examination are below other values. Higher values are possible to obtain because the exposure condition or exposure factor used are too large. This is because in this study there was not irradiation usage rules or guidelines in selecting exposure factor. The diagnostic reference level for medical exposure or DRL is highly recommended to use as a guidance for medical practitioners in optimizing protection for each type of diagnostic and interventional radiology examination. And it is used to prevent unnecessary radiation exposure to patients. As per Kabapeten number 4 of 2020 about radiation safety in the use of diagnostic and interventional radiology X-ray, state that the application, optimization of radiation protection, and safety to medical exposure, one of which must go through the level of diagnostic guidance according to national guidelines set by the head of the agency. However, DRL is not a value that determines whether radiology services are good or bad, but it is only an indicator of service quality. DRL is not a value indicating whether a patient has received an overdose. Patient may receive dose exceeding the DRL if medically justified and taking such doses is unavoidable. DRL can be used to check and manage patient doses so that patients receive the lowest possible dose achievable without compromising the desired image quality. In practice, if the patient dose exceeds the DRL, it has to be recorded and reviewed to find possible causes and proper corrective action option. Unless the dose is unavoidable and it has to be medically justified. The corrective action can reduce the dose to achieve the more dynamic DRL value, heading to the lowest possible dose. Conclusion. Based on the result and discussion, it was found that the estimated values of the patient radiation dose on 40 thoracic radiography show different value. The value of thoracic of PA and lateral examination was above the DRL value set by Bapeten, while the value of thoracic of supine AP examination got the value under the DRL value from the Bapeten. Further research is still recommended to develop the topic using irradiation rules or exposure factor selection guidelines. Acknowledgement. The author would like to thank for the help and encouragement from colleagues, as well as the Al-Islam Politeknik of Bandung institution for the financial support for this research. Thank you. Assalamualaikum warahmatullahi wabarakatuh.